Let me show you how to be a good Bayesian.
In this episode, I am thrilled to host Nate Haines, the head of data science research at Ledger Investing and a PhD from Ohio State University. Nate's expertise in generative and Bayesian modeling helps tackle the challenges in insurance-linked securities, especially with issues like measurement errors and small datasets. He delves into his use of state space and traditional time series models to effectively predict loss ratios and discusses the importance of informed priors in these models. Nate also introduces the baseline package, designed to enhance predictive performance by integrating diverse model predictions through model stacking. He also explains how they assess model performance using both traditional metrics like RMSE and innovative methods like simulation-based calibration, one of my favorites, to ensure accuracy and robustness in their forecasts. So join us as Nate unpacks the complexities of Bayesian modeling in the insurance sector, revealing how advanced statistical techniques can lead to more informed decision-making. This is Learning Bayesian Statistics, episode 115, recorded June 25, 2024.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PIMC Labs can help bring them to life. Check us out at pimc-labs.com.
Nate Haines, welcome to Learning Bayesian Statistics.
Thanks for having me. Very excited to be here.
Same. Very, very excited to have you here. Also because a lot of patrons of the show have requested you to be here. One of the most,
okay.
one of the most convincing was Stefan Lorenz. I'm pronouncing that the German way because I think he's somewhere from there. Maybe he's Austrian and or Swiss and like he hates me right now. But Stefan, thank you so much for recommending Nate on the show, and I hope you'll appreciate the episode. If you don't, this is entirely my fault and not Nate's at all.
Yeah, well, I appreciate the shout out, Stefan.
No, he was like really. He told me like that. Like, I'll tell you what he told me. He was, for a while now, I've been thinking about an interesting hook to recommend Nathaniel Haines, someone who is not, like so many of my previous recommendations, currently in academia.
Yeah.
Yeah, and he was like, today it seems to have presented itself. He just released a Python library for Bayesian model averaging, a very practical topic that hasn't been discussed yet in any episode. So, he was really, really happy about your work.
Very cool. Yeah, no, it's always fun to hear.
Yeah, and we are definitely going to talk about that today, model averaging and a lot of cool stuff on the deck. But first, can you tell us basically what you're doing nowadays, Nate, if you're not in academia, especially since you live in Columbus, which right. I think is mostly not for Ohio State University.
Right, yeah. We think of ourselves as a flyover state. Well, others think of us as that. We like to think that we're much cooler and hipper and, all that. But so I've been, for the last few years, I've been working as a data scientist remotely, and I've been at two different startups during my time the last few years after graduating from my PhD with my PhD focused on clinical mathematical psychology, where it's kind of really where I did a lot of the Bayesian modeling, where I learned a lot of Bayesian modeling, which led me to where I am today at so my current company. I'm with Ledger Investing, and we are sort of like in between what I would call like insurance industry and like finance in a way. We are not an insurance company, but that's the data that we deal with. And so a lot of our modeling is focused on that. And at Ledger, I'm the manager of data science research. So a lot of my work focuses on like building new models, productionizing those models, and finding out different ways to kind of incorporate models into our basically into our production workflow. And I'll be happy to dive into more detail about that, or kind of how I got here, because I know it's something I've talked to a lot of people about too, especially on the academic side. Like the transition to industry itself can be kind of something that's a little bit opaque, but then also like Bayesian industry is like, oh, I didn't know there was like people doing a lot of that. And so I'm excited to talk in more detail about all of that.
Yeah, for sure. Actually, how did you end up working on these topics? Because Bayes is already a niche. So then, like specializing in something Bayesian is even more niche. So I'm really curious about how you ended up doing that.
Yeah, just like Bayes in general. So I actually got exposed to Bayes like pretty early on. I guess you could say I have a weird background as a data scientist, because I did my undergrad degree in psychology, and I just did a BA, so I didn't really take much math in undergrad. But I got involved in a mathematical psychology lab, research lab, later on in my undergraduate degree. And this was run by Tricia Van Zant at Ohio State. So actually, I grew up in Columbus, and I've been here ever since. So, but I started to work with her and some grad students in her lab, and they were all, the best way to put it, they were hardcore Bayesians. So they did a lot of mathematical modeling of sort of more simple decision-making tasks. And by simple, I guess I just mean like like response time types of tasks. And so they did a lot of reaction time modeling, which has a pretty deep history in psychology. And so they were all Bayesians. That was the first time I saw the word. I remember seeing that word on like a grad student's poster one time. Like, what is that? And so I got exposed to it a bit in undergrad. And then when as I was going through undergrad, I knew I wanted to go to grad school. I wanted to do a clinical psychology program. I was really interested in cognitive mechanisms, things involved with mental health. And I got really lucky because there was an incoming faculty at Ohio State who, Woo Young An is his name, and he was the one he brought a lot of that to Ohio State. He didn't end up being there for too long, but he's now at Seoul National University. But I worked with him for a year as a lab manager, and in that first year, he really wanted to build some open source software to allow other people to do decision-making modeling with psychological data. And the way to do that was to use hierarchical Bayes. And so I kind of got exposed to all of that through my work with Young. And we did a lot of that work in Stan. And so that was kind of like the first time I really worked on it myself. But I'd kind of known about it and knew about some of the benefits that Bayes can offer over other philosophies of statistics. And that started pretty early on in grad school. So I think I'm probably a weird case because I didn't really have like traditional stats training before I got the Bayes training. And so a lot of my perspective is very much I think a lot in terms of generative models, and I didn't have to unlearn a lot of frequentist stuff because my understanding by the time I really started diving into Bayes was pretty rudimentary on the frequentist side. And so, that kind of naturally, I got really involved in some of that open source work during graduate school on the package we released called HBayesDM, which is a mouthful, but really good for search because nothing else pops up if you search age-based EM. And and so that was kind of my first foray into like open source Bayesian modeling types of software, and that eventually, like I decided that I really like to do this method stuff. It was more focused on the modeling side of my work than I was on like the domain per se, and had a really interesting kind of uh, track into industry. I wasn't actually originally pursuing that. That wasn't my intention, but I just got a cold email one day the summer I graduated from a co-founder at my previous company, which is called Avo Health. And they were looking for someone who did something very particular, which was like hierarchical Bayesian modeling. They were familiar with psychological data, and so I kind of fit the bill for that. And I decided that it'd be worth a shot to try that out. And I've been in industry ever since. And so yeah, I think it was really what got me into it originally was just kind of being in the context surrounded by people doing it, which I don't think most people get that experience because Bayes is still, yeah, rather niche, like you said. But at least in the circle that I was in undergrad and grad school and things like that, it was just kind of the way to do things. And so I think that's colored my perspective of it quite a bit, and definitely played a big role in why I ended up at Ledger today.
Yeah, super cool. Yeah, and I definitely can relate to the background in the sense that I too was introduced to stats mainly through the Bayesian framework. So thankfully, I mean that was hard, but that was not as hard as having to forget everything again. You know, so
right.
It was great. I remember being very afraid when I opened a classic statistics book and was like, oh my god, how many tests are there? It's just
right.
terrible.
No, exactly, and it's hard to see how things connect together, right?
Mm-hmm. Oh yeah, no, I was not liking stats at all at that point.
Right.
And then thankfully I did electoral forecasting, and you kind of have to do Bayes in these realms. So that was really cool. That one of the best things that ever happened to me.
Yeah, exactly. So you're forced into it from the start. It doesn't give you much choice, and then you look back and you're happy that ended up happening, right?
Exactly. Yeah.
Yeah.
And actually, you do quite a lot of time series models, if I understood correctly. So, yeah, could you talk a bit about that? I'm always very interested in time series and forecasting models and how useful they are in your work.
Yeah. So I think maybe first to start, like I can give a bit of context on kind of the core problem we're trying to solve at Ledger, and that'll help kind of frame what we do with the time series models. So like basically what we provide is an alternative source of capital for insurance companies. And so it's like, if I wanted to start an insurance company, I'd have to have a ton of money to like have in the bank so that when people are, if something goes wrong and I write a bunch of policies for private auto, for example, for car insurance, I have to be able to make people whole when, an accident happens. And so when insurers are trying to fund different books of business, they need often to raise lots of capital for that. And traditionally, one of the methods that they have done to accomplish this is to approach reinsurers, which I didn't know anything about before I joined Ledger. I'm kind of an insurance newbie at Ledger. Well, now it's been a couple years, so I can't say that anymore. But basically, go to like someone with even more money to kind of provide the capital and kind of allow them to write their business. And so we we basically work with insurers or other similar entities and then investors and allow the investors access to this insurance risk as like an asset class. And then from the perspective of the insurance side, they're getting the capital that they need to fund their programs. And so it's sort of a way for the insurance companies like it because it's the source of capital they need to do business. The investors like it because they get to invest in how these portfolios of insurance programs are performing, as opposed to, like, say, investing in an insurance company stock or something like that. And so it's a little bit more uncorrelated with, like, the market in terms of like other types of assets that investors might have access to. And so that's kind of the core problem our data science team is, like the context that we're baked within, and what we're actually modeling, like the thing we're trying to solve is, so we have, say, an insurance company approaches us and they have a commercial auto or a private auto program or a workers' compensation program. So a lot of times they'll have, like, been writing that kind of program. They've been in that business for 5-10 years or something, and so they have historic data. And the way we look at the data is you have like different accident years. So if you think, like, if we're looking at it today in year 2024, maybe they have like 10 years of business that they've been writing. And so we look back all the way to like 2014, 2015, 2016, and we see how much have they lost, like how much claims have they paid out versus premium have they taken in. And so there's this quantity of, like, the loss ratio is really important. And in a lot of areas of business, it's like around a 60%. And this is before, like, you're paying salaries and all of that. Just like the pure, like, insurance side, like around 60% might be pretty typical, or pretty reasonable for, like, a good-ish program. So it's an overgeneralization, but just to keep some numbers in mind. And the interesting thing about this, though, is that we look back at 2014 and we have 10 years of history. So we kind of know what the loss is for 2014 for a program that comes to us today. But what of, like, 2023, right? There's only been a year since then. And the way that insurance often works, if you've ever had to file a claim for, like, homeowners or car insurance, something like this, you're probably familiar. It can take quite a while for you to get paid out. And sometimes there's lawsuits. Sometimes people don't file a claim until years later. Like, there can be a lot of different reasons that the information we have today about losses in any given year maybe isn't complete, or the way that we think about it is the loss ratio isn't developed. And so if you think about, like, the data that we have, it kind of takes the shape of this triangle where and we call them loss triangles, where you have, you can think of like a matrix where the sort of X or the y-axis would be the accident years, so the different years that accidents are occurring. And then the x-axis would be how much time has passed since we're looking at that accident year. So we call that, like, the development period or something similar. And so, like, 2014, we have 10 cells, 10 years of data that we can look back on. 2014, we have 9, and so on and so forth. And so it kind of forms this triangle. And so basically, for us to price these deals, what we end up needing to do is two things, and there's kind of two basic, like, modeling steps involved. And the first is to find out, where do we think the loss ratio is going to end up for all of these accident years, like if we were looking back, like 100 years from now. And so we want to know, like, what that ultimate state of the loss ratio is. And so that's the first part where some time series models come into play. And so we have this kind of weirdly shaped data, and we want to extrapolate out from historical to kind of we're thinking about the year as being static that we're looking at, but, like, our information that we have on it is dynamic, and we can learn more about that as time goes on. And so our first task is to kind of predict that ultimate state, and that just gives us a sort of more accurate representation of what we think the history will look like. And so that's our first step. And then the second step, which is where we use much more traditional time series models, and the second step is to then say, okay, given that history of, like, the ultimate state for each previous year, like, what are the next 2-3 years going to look like? And that's where we have more traditional forecasting models. But because we have this multi-stage process, like, there's uncertainty from one model output that we need to account for in that second stage. And so we have, like, we do some measurement error modeling and things like that. And that at the end of the day is really why like Bayes ends up being such a useful tool for this problem, just because there's lots of sources of uncertainty. There's a rich history of actuarial science where actuaries have developed models to solve similar problems to this. And so there's like theory-informed models, there's historic data that we can use. And so we get to use really everything in the Bayes toolbox. Like we get to use priors, we get to use very theory-informed generative models. And then we also get to do some fun things like measurement error modeling and things of that nature, kind of between the various stages of the modeling workflow that we follow. So I know that was kind of a long explanation, but I think the context is kind of helpful to understand like why we approach it that way and why we think Bayes is a useful way to do so.
Yeah. Yeah. Thanks a lot for that context. I think it's very useful because also then I want to ask you about, then which kind of time series models you mostly use for these use cases, and what are some of the most significant challenges you face when dealing with that kind of time series data?
Yeah, no, it's a great question. So I'd say like the time series models, we do a lot of state space modeling, and so we've done it really kind of like we do a lot of research on exploring different forms of models, but the stuff that we end up using in production, like that first stage where we do our kind of development process, those models are more similar to like the classic actuarial science models. So they technically are science or time series models, but they're kind of these like non-parametric models where we're just estimating, say your loss is 20% during the first development lag, what can we estimate some parameters that if you kind of multiply that by some factor, that gives us the next period. And so there's these link ratio style models that we use in that context. And so that's a little less traditional, but more in line with what actuaries have historically done. And then for the forecasting piece, that's where we use more kind of modern, more classical, or not classical, but more what you would imagine when you think of time series models today. So things like autoregressive styles of models. We do, like I said, some state space models where we kind of assume that these loss ratios are really this latent kind of drifting parameter over time, and then we have sort of the latent dynamics paired with some observational model of how those losses are distributed. And then a lot of times in like the investment or like the finance world, people talk about whether they think some sort of asset is mean reverting or if it shows some sort of momentum in the underlying trends. And so we have different models that capture some of those different assumptions. And actually pretty interesting, like people all across the business tend to be pretty interested in, whether a model has mean reversion in it or momentum in it. And that becomes actually a question that a lot of investors and insurance companies alike are interested in knowing, because they might have disagreements about whether or not that component should be in the model. But so I'd say like those types of time series models are what we use most regularly in production. So like your traditional state space models. That in like terms of the challenges we face, I think the big challenge is that kind of based on the context that I was providing, we might have like 10 years of history on a program, and that would be a good outcome. And so, if our time series is 10 previous data points, where some of the more recent ones are highly uncertain because they're actually, they're predictions from a previous model, that I think you might kind of start to imagine where the issues can arise there. And so I think I would say that's probably our biggest challenge is the data that we work with from a given program. Like the numbers are big because we're talking about like investment, like amounts of dollars. So, a program might write $10 to $100 million of premium. And so like the loss values are pretty high themselves, and so it's a lot of information there. But like the history that we have to build a time series model on is pretty short, and so a lot of like classical time series approaches, there's quite a bit more data that people are working with. You'll hear about like things with seasonality and other types of things where you're decomposing a time series. And we don't really have the ability to do any of those classical modeling approaches, mostly just because we don't have the history for it. And so one of the ways that we approach that problem to help solve it, and at least in some to solve it to some extent, is that we do have information on many different insurance companies and their losses historically. So even if the history may not be very long, like we might have like at maximum, I don't know, 30, 40 years of history, 50 years of history sometimes on it was like 50 basically individual data points in a time series model. Typically we have much less, but one of the things that happens in the insurance industry is that all of these companies, they need to publicly release certain information each year. And so we're able to use that to basically we're able to take that information and use it to help us obtain data informed priors. And so that when a smaller program comes our way and we are using our time series models on that, we have priors that have been pretty fine-tuned to the problem. And so like priors that are fine-tuned to that particular line of business, whether it's commercial auto or workers' compensation or something like that. And so I'd say that's like our biggest challenge is that small n kind of problem. And then Bayes with the informed priors is a way that we're able to tackle that in a more principled way.
Yeah, that makes a ton of sense, and that sounds like very fun models to work on.
Yeah,
I really love that. So state space models, you're mainly talking about HMMs, things like that? Or
yeah, some of the
GPs?
same form. Yeah, we've done some experimenting with with Gaussian processes. Actually, about to submit my colleagues about to submit a paper doing some work with HMMs, which are hidden Markov models for anyone who's listening, I guess, maybe who might not know what that acronym stands for. And but typically the models that we use end up being even more simpler than that for our forecasting problem, mostly just because of the fact that we do have such a small data to work with. Oftentimes, like the functional form of the model can't be too complex, and so they end up being kind of more similar to your typical like ARIMA style models, which you can kind of write in a state space fashion. And so that it tends to be more closely related to those than models that do like regime switching and things like that, because oftentimes we just don't have enough information to be able to fit those types of models. Even with informed priors, it might not be as believable. That being said, it's one of those things that like if we do think that something might work well, like if we think that adding a more complicated mechanism on the momentum piece of the model, or adding in different assumptions about mean reversion and things like that, we typically do explore those types of things. But surprisingly hard to beat simple time series models with the small n in our context, and so we do quite a lot of cross validation to determine which types of models we should be using in production, and oftentimes it's a mix of evaluating those models based on their performance, but also how well calibrated they are and things of that nature, so that we know that the models we're using are interpretable and we can kind of defend them if something ends up going sideways. We want to be able to go to the investor and say, like, we did our due diligence and here's why we think this was still a good choice at the time. So I'm not sure if that gets at that question, but let me know if I can expand on the models in particular.
No, I mean, that's funny you'd say that, because definitely it's hard to beat. It's surprisingly hard to beat regression in a lot of contexts. Right? Like if you
Right.
do a good generalized regression, that's already a very good baseline, and that's pretty hard to beat. So I'm not
Yes,
surprised to
yeah,
hear that's the
exactly.
same here.
Right. And I think part of the issue too with our data is that like the more recent observations in the time series have this high uncertainty along with them. So with the measurement error component in there, it's difficult to choose between different model configurations. And so the more complicated your forecasting model is, that uncertainty ends up kind of making it even harder for a more complex model to win out in our tests. And so that's one of the things that we've observed, and something that I think probably anyone who's been involved in similar contexts would be able to say they've run into as well.
Yeah, yeah, yeah. And well, actually, I want to make sure we we get to model averaging and comparison. So I still have a few questions for you with time series and these kind of models, but let's switch gears a bit here and like tell us how you use Bayesian model averaging in your projects, and what advantages do you see in this approach over single model predictions?
Yeah, no, it's a good question. So I hadn't done a ton of work with Bayesian model averaging or model averaging in general before I joined Ledger, and so I was really excited to get to work on some of that stuff. And one of the ways I'd say it comes up in multiple parts of our workflow now, but one of the first use cases was for our forecasting models that I was describing a bit earlier. We we have different models that make different assumptions about the underlying losses and how they might change over time. And I think the one example is like does the process have momentum or not? So like if a loss ratio is trending upward, do we think it's going like is there going to be some component of the model that kind of keeps it trending upward over time versus do we have something in there where it functions more like a random walk? And and this is something that a lot of industry experts might debate, or like if you're if you're like an actuary or a CEO of some insurance company and you're trying to explain like why your losses are or trending in a certain direction, like people talk about these things pretty normally, like momentum or reversion, things like that. And so, so because people have varying opinions about this, our approach, one approach would be to try different models that make those different assumptions, and then do some model comparison and just select one. But the because often there's certain contexts where it might make sense to assume a momentum, it might make sense to assume reversion, and then other contexts where it might not. Um, but model averaging became kind of like a very natural thing to do and try out in that context. And so that was really what inspired it, is just this idea that we don't have to necessarily choose a model. If we think both are reasonable, we can allow the data to make that decision for us. And so that's really where it came into our workflow. And when we're doing our forecasts, we'll have these different models that we fit and make predictions with, and then we have our model averaging models, which now talking about models of models gets a little bit fun terminology wise. But that's the stage where we bring those in and we say, like, okay, given, we might have some covariates that we can use to build those models, those averaging models. And so things like we know what line of business it is, it's commercial auto, workers' compensation, something like that. Like we know how like big the volume is, like how much premium that the program brings in. We know like locations of these different businesses, and so all of those can then be used as covariates in like a stacking model, for example, and we can train those models to combine, rely more on the assumptions of one model over the other, depending on the context. And that was the motivation, and that's where we still do that work today, is mostly at that forecasting step. Um, But yeah, no, I think Bayesian model averaging is really nice because if you have the capacity to be able to fit the models that you want to blend together, then I mean, we found through our research, if we do that and compare it to like a single model in isolation, not always, but oftentimes it will end up performing better. And so it's sort of like a why not take the best of both worlds as opposed to having to worry about model selection, and especially when the underlying models that we're blending together are both like equally theoretically motivated, and it's hard to really make a decision, even if the data were to suggest one over the other.
Yeah, I mean, that definitely makes sense. If you have a bunch of good models, that's really cool to be able to average them. I remember when I started learning Bayesian stats, I was really blown away by the fact that this is even possible.
Yeah.
And that's just incredible. Can you contrast model averaging with Bayesian model comparison to make sure listeners understand both concepts and how they fit together, and then talk about how you implement these techniques in your modeling workflow?
Yeah, no, great question. I think so. When I think of Bayesian model comparison, I often think of different types of metrics that we might have, whether it's approximations or done by brute force. We might have some sort of cross-validation metrics that we evaluate the models on. So, like in our forecasting case, we might have actual historical, maybe we have actual data from like 2000, and so we actually have like 10 years of history on it. We know what the ultimate state is. We know what like the forecast should predict. In those cases, we can train our models. We can have them do the out of sample predictions, and then we can score on those out of sample predictions, like how well they're performing. So we often actually do the brute force as opposed to doing something like I know in the STAN community, you might have like the Pareto smooth importance sampling, leave one out, approximations, things like that. Is another way to approach the problem. But basically, a lot of times when you're doing Bayesian model comparison, you'll have some out of sample metric or approximation to it. And then you might have that for a bunch of out of sample data points. And then those data points, you can do some statistical tests or even just look at sort of absolute values of how much better one model is predicting the out of sample performance metrics versus another. And in the STAN community, and in PyMC as well, I think like the expected log pointwise predictive density, or the ELPD, is a quantity that's often used, which is sort of a log likelihood based metric that we can use on out of sample data to compute like expected predicted performance. And typically for Bayesian model comparison, the practice almost stops after you get that ELPD value or something similar. It might be, you might do some test of like how different they are, like some standard error on the difference of the ELPD between two models. But at the end of the day, like once you have that metric, that's sort of the inference that you might have at the end is that, okay, this model is performing better per this metric. And with stacking, what you're doing, I guess there's different forms of model averaging. You have like Bayesian model averaging, which is slightly different than stacking and things like that. But all of them follow the same basic principle, is that you have your out of sample performance metrics, and then what you do is, instead of just choosing one model based on the model that has better out of sample performance metrics, you build a model on those performance metrics to kind of tell you when you should rely on model A versus model B. And so these stacking or averaging models we can think of as just like a different model themselves that are trained, instead of on your outcome measure and your actual substantive or your candidate model that you care about. It's trained on the performance metrics, the out of sample performance metrics that you are using to, in this case, you wouldn't be doing model selection. You'd be blending together the predictions from each of your candidate models according to the model and how it thinks you should weight both based on the out of sample performance. And so, so kind of going that route does require a bit more. You have to think a little bit more about like how you're using your data, because if you want to evaluate how well a stacking model is performing, for example, you have to leave out a little bit more validation data. So you don't want to do any double dipping, and so you'll have your candidate models that you'll make out of sample predictions on. Those predictions become your performance on those predictions become the basis for training your stacking model. And then at the end of the day, you might train your stacking model on some other, third validation set of data. And so I think that's really the only big limitation, I would say, of using those approaches over just like your traditional model comparison, where you're kind of done once you select your model. That being said, I think, being able to combine the predictions from the candidate models ends up oftentimes being well worth kind of dividing your data up that way.
Yeah, definitely. That's an extremely good point, and also very useful method. And I know in PyMC, for instance, with RVs, you can do that very easily, where you basically do your model comparison with RVs. It's going to give weights to the models, and then those weights are used by PyMC with the pm.w sample posterior predictive _w, where we weight each model's predictions, each model's posterior predictive samples according to the weights from the model comparison. So is that how you usually end up implementing that, or are you using Stan? How do you do that? I think it's going to be interesting for the listeners who want to give that a try.
Yeah, no, it's a great question. So no, that's a good plug for the paper we just wrote. We've been actually using some internal software to do a lot of this. So like actually all of our software historically has been like we have our own kind of BRMS is not the right term for it, but like we have our own language that we use to write Stan models, and then we do a lot of our like stacking and stuff. We had our own like internal code that we would use to do all of this. But we decided recently that this was something that, like I think we were talking about before the show started today, that it's not something that has gotten a lot of attention, like in terms of like making this easy to do in a generic way with like a bunch of different types of stacking models. And so we've actually just released and wrote a paper on this package in Python called Bayes Blend. And what this package, the intent and what we hope that it will allow users to do, what allows us to do it at least, so hopefully other users as well, is like given, I might have a model that I fit in Stan or PyMC or, whatever probabilistic programming language of choice. We have built the package such that you can kind of initialize a stacking model, one of a various different ones. So we have like the pseudo Bayesian model averaging types of models, the pseudo BMA plus models, which are things that are based on the ELPD, and they blend based on that. And then we also have like proper Bayesian stacking and hierarchical stacking models that you can use with Bayes Blend, where given the out of sample likelihood metrics that you can get by training your data or training your model on one set of data, making out of sample predictions on another test set, given those as input, you can fit a variety of these different stacking models and then easily blend them all together and evaluate performance and things like that. And so we've built that in Python just because that's the stack that like we use Python for our day-to-day work and in our production setting. And then we've been building integrations so that like right now it's really easy to interface with command stand because that's what we use. So we kind of built from that perspective first, but it does interface with RViz as well. So if you're using like PyMC, for example, you can like you can kind of create that RViz inference data object and then use that as input for Bayes blend. And then, yeah, what you'll get at the end of that workflow, if you use Bayes blend, is you get the blended predictions from your candidate models, as well as the blended likelihood, like the posterior likelihood, which you can use then to evaluate performance and things like that. And so, yeah, we're really excited about this. I'm really excited to get other people outside of Ledger to use it and tell us what they think. Make some complaints, submit some issues. There's a discussion board on the GitHub page as well. And we have a paper that we've submitted to, we have a preprint on arXiv, and we've submitted the paper as well to the journal, see how that goes. But it's something that we use regularly, and so it's something that we plan to keep contributing to. And if there's like quality of life or convenience things to make it easier for other folks to use, we'd love to hear about it. Because I think there's a lot of work that can still be done with stacking. There's a lot of really cool methods out there. I think hierarchical stacking in particular is something that I haven't really seen used much in the wild. It's something we use every day at Ledger, which I think is yeah. So I'm hoping Bayes blend will allow other people to kind of see that benefit and apply it in their own work easily and in a reproducible way.
Yeah, this is super cool. And so, of course, I put in the show notes the paper and the doc, the documentation website to Bayes blend for
Awesome, yeah.
people who want to dig deeper, which I definitely encourage you to do. And when you're using Bayes blend, let's say I'm using Bayes blend from a PIMC model, so I'm going to give an inference data object. Do I get back an inference data object with my weighted posterior predictive samples? How do I get back in which format am I going to get back the predictions?
Yeah, that's a great question. I think if I can remember correctly, I don't want to give you the wrong information. I'm pretty sure we have like when you create the object that does the stacking, so the model object, there's a from RViz method, and then I think we have a to RViz method that you can kind of it will use its own internal representation of the like predictions and things like that for just the sake of like fitting the stacking model. But then I think you can return it back to an RViz inference object at the end. And one of the things that I want to do, we haven't had the bandwidth for it quite yet, but it's not that many steps to then just kind of get rid of like we should just have like a from PyMC method, for example. And I think implementing something like that would be pretty straightforward. So I think we'll probably get to it eventually, but if anyone else wants to contribute, won't say no to that. We have that doc on like how to contribute as well on the GitHub page. So, but yeah, so I think our intention is to make it as seamless as possible, and so to the extent that there's ways that we can make it easier to use, definitely open to add those features or take recommendations on how we should approach it.
Okay.
But yeah, I think probably right now working through the RViz inference data object is the way you can interface with most things other than command stan.
Yeah. I mean, for people listening in the PyMC world and even Python world and even Stan world, investing in understanding better the inference data object and XRA is definitely a great investment of your time, because I know it sounds a bit frustrating, but it's like basically it's like pandas. It's the pandas of our world, and if you become proficient at that format, it's going to help you tremendously in your Bayesian modeling workflow, because you may only want to interact with the model, but actually a huge part of your time is going to be making plots, and making plots is done with prior predictive or posterior predictive samples, and that means they live in the inference data object. And I know it can be a bit frustrating because you have yet another thing to learn, but is actually extremely powerful because it's a multi-dimensional pandas data frame, basically. So instead of only having to have 2D pandas data frames, you can do a lot of things with a lot more dimensions, which is always the case
Right.
in
No,
statistical
I would
models.
totally agree with that. And
So
I
yeah,
think the other thing that's nice about it is like you can use it in it. They have integrations in RViz to work with a whole host of different PPLs. So it's like,
yeah,
whether you're using Stan or
yeah,
PyMC or whatever else, like if RViz data inference object is always like the commonality, it makes it easy if like, oh, I'm in a different setting and I'm using this other PPL in this case, and having to learn a bunch of different tools to do plotting and deal with the data can be quite annoying. So it's nice to have one place to do most of it. And I think we're going
yeah.
to lean on that pretty heavily with like developing base blend. Like I think there's more we could probably do to integrate with the inference data structure and like in terms of like making it easier to plot things and stuff like that. So I think
Yeah.
it's something I'm learning more and more about myself and would, yeah, definitely also recommend others to do.
Yeah. That's what I tell my students almost all the time. Is like time spent learning how inference data object works is well spent. That's
Yeah,
really,
agreed.
because you're gonna have to do that anyways, so you might as well start out.
Right,
Yeah.
right. Yeah. You'll encounter it
And
at some point.
yeah. And I'm wondering. So you talked about model stacking too. I'm not familiar with that term. Is that just the same as model averaging, or is that different?
Yeah, I mean, so there's technically some differences, and I think some of the ways that like when I think historically the term Bayesian model averaging has meant something pretty specific in the literature. Um, and yeah, I want to hope to not get this wrong because sometimes I mix things up in my head when thinking about them. It's just due to the names makes it easy. But I'm pretty sure historically Bayesian model averaging was done on like in sample fit statistics and not out of sample, which can kind of it's a small thing, but it can make a big difference in terms of like results and how a problem is approached and things like that. And so when talking about model averaging, I'd say like stacking is one form of model averaging. And there are many ways that one could perform model averaging, whereas like stacking is one specific variant of that. And like the way that we like actually implement stacking is there's a couple of different ways that you can do it, but you're basically optimizing um, the like if you have the out of sample log likelihood statistics, you can compute like a pointwise ELPD, if you will. So it's not like the sum of the log predictive density across all of your data points, but just like each data point has its own LPD. And then what you're essentially doing with stacking is you're fitting a model to optimize combining all of those points across your different models. So it's like, maybe for certain data points, yeah, model A has a higher out of sample likelihood than model B, and for others it has lower. And so the goal of the stacking model is to fit it to those with those as outcome measures, and then the weights that you derive from that are basically just optimizing how to combine those likelihood values. And so um, and so the way that stacking is actually implemented after you estimate those weights is to like sample from the posteriors. So if I have like for a given data point, I have a 50% weight on one model, 50% weight on another, kind of blending together the posteriors by drawing samples in proportion to the weights. And so that's kind of how stacking is approached and how we've implemented it in Bayes Blend. And I know like pseudo BMA, I think Yuling Yao, who had done a lot of work with stacking and pseudo BMA and stuff, we've had some talks with him, and as well as Aki Vatari and some other folks who've done some work on these methods. And I think they're moving away from the pseudo Bayesian model averaging terminology to start to to call it something that is less suggestive of like what classical Bayesian model averaging has typically referred to. And so I think like for folks interested in exploring more of that today, I mean, you can read the preprint does some definitions that does a pretty good job, I'd say, of kind of defining some of these different ideas and gives you the math that you can look at to see how it's actually done mathematically. But then if you're kind of searching for resources too, I think focusing on like the stacking terminology should be probably pretty helpful over like Bayesian model averaging. That's my 2 cents at least.
Okay, yeah. So what I get from that is that it's basically trying to do the same thing but using different approaches.
Yeah, right. And that's my impression. I'm sure other people will have different reads on the literature. Like I said, it's something I've only really begun to explore in the last couple of years, and so I'm sure there are many other people out there that know much more.
Okay, yeah, for sure. If we said, if we've made a big mistake here and someone knows about that, please get in touch to me. You can be outraged in your message. That's fine. I will learn something from that, so I welcome it.
That's right. Me as well.
And so actually, I'd like to get back a bit to the previous models. We talked about, now that we've talked about your model averaging work, and I'm curious about how do external factors like economic downturns or global health crises, for instance, how does that affect your forecasting models, and what strategies do you employ to adjust models in response to such events?
Yeah, no, it's a great question. So yeah, economic factors definitely can influence kind of the performance of these portfolios, but a lot of times it's actually surprisingly like these loss ratios are surprisingly robust to a lot of these economic factors, and partly it's just because of the way that I think insurance generally works, where if a good example of this is in like COVID times, people like for example, if you're thinking about insuring commercial auto or private auto insurance policies, and like when COVID happened, people stopped driving, and so people got into a lot less accidents, and so in that case, loss ratios went really far down for auto policies or for auto programs, and in some cases, insurance companies actually paid back some of the policyholders, like some portion of the premium, just because things were so like things the loss ratios were so low, and so there's examples of things like that happening, but like just due to the nature of how like policies are written out, you do have to have and how they're paid out. So like I pay my insurance up front, and then I only like they only lose money when claims are made. The things that we think about, they have to be mostly things that would influence claims, I would say, is the primary factor. So if there's something economic that we believe is going to affect how much claims are made, whether we think it will make them go up or down, like that's going to be the primary force through which like economic conditions could affect these models. Mostly because like the premium that is written is pretty stable. Like generally, regardless of what's going on economically, the same types of insurance policies like are often either required or things like that. So unless management is changing a lot about the program in terms of how they're pricing things or something of that nature, you don't tend to get huge swings in the premium that's coming in. And so that's what we focus on mostly, would be things that affect claims. And when we do look at that, one of the things that we've implemented, that we've looked into, is we look at like modeling overall industry level trends and using that as sort of input to our program level models. And so it's not quite like deriving priors from industry. It's more like we actually know across, all of the commercial auto programs, for example, what the sort of industry level loss ratio. And if we can understand, like that's where we might have some general idea of how economic factors might influence like something at that high of a scale. So like the interest rate environment or like the location of the industry and other things like that. We've built some models of like industry level trends that are then used as so it's like given we can predict like an industry loss ratio for the next so many accident years, we can use that information in our program level models and say like how much do we think we need to weight, the industry, where the industry is trending versus what we see in this program. And that's kind of how we've approached that problem historically. I'd say we approach it that way mostly just because it's really hard at the level of granularity that a lot of the programs that we deal with, like they're pretty small relative to industry at large. And so it's often hard to observe like general industry trends in the data, especially when we have, relatively few historic data points. It's hard to do it in a data-driven way. And so that's the big way that we've approached that problem is to kind of, if we can better understand industry and understand how economic factors influence where the industry is trending, we can then use that information in our program level analysis. And so we do have some models that do that.
Yeah, fascinating. I really love that. That's super interesting because like by definition, these events are extremely low frequency, but at the same time, they can have a huge magnitude. So you would be tempted to just forget about them because of the low frequency, but the magnitude means you can't really forget about them.
Right.
And so that's really where I think also having done that in the Bayesian framework is actually very helpful because you can actually accommodate that in the model.
Yeah, and I think that too, another thing that is kind of interesting about the kind of insurance portfolios that we deal with is that some of this is actually on the underwriters or the management team who's actually like writing the insurance policies. And so a lot of times like those folks are the ones who are way ahead of the game in terms of like, oh, I think there's this really what we might call a long tail risk or something like historically in like workers' compensation, asbestos was an example of this, where it was something that was introduced in a bunch of houses. It was used everywhere as an insulator. And, decades down the road, come to find out that this stuff is causing cancer and doing horrible things. And like those long-tailed risks they're pretty rare. You don't come by them often. But it's something that a lot of times the underwriters who are kind of pricing the policies and writing the insurance policies, they are sort of the frontline defense for that because they're on the lookout for all of these, long-tailed risks and taking that into account when like pricing the policies, for example, or when writing the policies themselves to exclude certain things if they think it shouldn't apply. And so oftentimes like that kind of makes its way into the perspective we have on modeling, because when we're modeling a loss ratio, for example, our perspective is that we're almost trying to evaluate the performance of the management team because they're responsible for actually, writing the policies and, marketing their insurance product and all of that. And we view ourselves as looking at the historic information as just like their track record. And so, I mean, that doesn't stop big economic things from changing that track record, but that's something that's kind of influenced how we think about our models at least from a generative perspective. And yeah, I think it's definitely important to have that perspective when you're in such a case where the data that you're getting is made and it kind of arises in a rather complicated way.
Yeah, fantastic points, Nate. I completely agree with that. And are there some metrics or well, techniques we talked about them, but are there any metrics, if any, that you find most effective for evaluating the performance of these Bayesian time series models?
Yeah, no, I think yeah, historically we've done a lot of the sort of log likelihood based metrics. So we use ELPD for a lot of our like decision making. So if we're exploring different models and we're doing our stacking workflow and all of that, at the end of the day, if we're deciding whether it's worth including another candidate model in the stacking model in production, we'll often compare like what we currently have in production to the new proposed thing, which could be a single model, it could be some stacked models or what have you. Typically, we're using ELPD, and we also look at things like RMSE and mean absolute error. We tend to not rely necessarily on any given metric just because sometimes, especially with ELPD, with the types of models we work with, there are some times where you can get pretty wild values for ELPD that can really bias like like at the end of the day, I guess this gets a little technical, but you might have an LPD score for each data point. And if one of those data points is quite off, when you take the sum to get your total model performance metric, it can sometimes, it acts like any outlier and can kind of make the sum go in one direction quite a bit. And so sometimes ELPD might be very sensitive to like outlier data points compared to things like RMSE. So you might be actually, and then the reason is just because like your prediction might be pretty close, like in an absolute scale, but like if your uncertainty is really low in your prediction, like what ELPD really is measuring is like the height of your posterior density, prediction density at where the data point is. And so if you're too certain, your data point's like way out in the tail of some distribution, and it ends up getting this crazy value, even though like RMSE might be pretty good because like on average you're pretty close actually. And so we have had to do some like I guess forays into more robust ways to compute or to kind of estimate ELPD. So we've done some research on that, and sometimes we'll use those metrics in production where we will say instead of taking a sum of the ELPD values across all your data points, say out of sample data points, will fit like a t distribution to all of those data points. And that's one way that like the expectation of that t distribution is not going to be as influenced by some extreme outliers. You also get the benefit of you get like a degrees of freedom parameter estimated from the t distribution that way, and that can be a sort of diagnostic because if it's too low, then you're approaching like a Cauchy distribution that doesn't have an expectation and doesn't have a variance, and so we've explored methods like that we'll sometimes use in production, just because we do so many tests, it's a shame to like not be able to do a comparison because there's like a few data points out of the thousands of data points that we have in our historic database that kind of throw everything off and make it such that like there's no consensus on which model is performing better. And so, yeah, that's a long way of saying we mostly focused on ELPD, but use some other like more absolute metrics that are easily interpretable, and then also some what we kind of think of as these more robust variants of ELPD, which I think at some point I think we'll try to like write a paper on it, see what other people think, because one of those things that it comes up, you come up with a solution to something that you think is a pretty big problem, and then very curious what other people might actually think about that, or if they see any big holes in the approach. And so I think, yeah, maybe at some point we'll have a paper out on that. We'll see.
Yeah, that sounds like fun. But actually, I think it's a good illustration of something I always answer my students who come from the statistic framework. And they tend to be much more oriented towards metrics and tests, you know. And that's always weird to me because I'm like, but you have posterior samples, you have distribution for everything. Why do you want one number? And actually, you worked hard to get all those posterior samples in distribution. So
That's
why
right.
do
Why
you
throw
want
them
to
away?
throw them out the window as soon as you have them? I'm curious. So yeah,
I need
like
to make a
often
decision, right?
yeah. And often they ask that, like, something related to, but what's the metric to know that basically the model is good? So
Right.
how do I compute R squared, for instance?
Right.
And I always give an answer that must be very annoying, but that's like I understand that you want a statistics, a metric, a test statistic. That's great. But it's just a summary, right? It's nothing magic. So what you should probably do in all of the cases is using a lot of different metrics, and that's just what you answered here. Is like you don't have one go-to metric that's supposed to be a magic number, and then you're good. It's like, no, you're looking at different metrics because each metric gives you an estimation of a different angle of the same model, and a model is going to be good at some things but not at others, right? It's a bit like an athlete, right? An athlete is rarely extremely complete because it has to be extremely specialized. So that means you have trade-offs to make, and so your model, often you have to choose, well, I want my model to be really good at that. Don't really care about it being really good at that. But then if your metric is measuring the second option, your model is going to appear really bad, but you don't really care about that. So what you end up doing as the modeler is looking at the model from different perspectives and angles, and that will also give you insights about your model, because often the models are huge and multi-dimensional, and you just have a small Homo sapiens brain that cannot see beyond 3 dimensions, right? So you have to time down everything, and basically I'm always saying, like, look at different metrics, don't always look at the same one, and maybe also sometimes invent your own metric, because often that's something you're interested in. You're interested in a very particular thing. Well, just invent your own metric, because you can always compute it, because it's just posterior samples, and in the end, posterior samples, you just count them and you see how it goes. That's not that hard. I
think that's great. It's great to like get that in folks' heads when they're like starting to learn about this stuff. It's like I can't even I can't even count like how many classic like machine learning papers I've seen where you just have tables of bolded metrics where the model with the lowest RMSE is the best, right? And so therefore it's chosen. And I think that perspective can make it a little harder to actually understand your models for sure. And yeah, because there's even other things like it reminds me, like, yeah, I mean, we look at, like, we do simulation-based calibration, like prior sensitivity analysis, like all of these things that aren't necessarily tied to a performance metric, but they're tied to how well you can interpret your model and how much you can trust it and the parameters that it's outputting. And so I think like all of those should also definitely be considered. And another thing that we encounter quite a lot is like there's a cost to productionize these models. Like if we have a new model and it performs better technically by a small amount, like is it really worth it if it's like very complicated, hard to interpret, and hard to maintain? And I think sometimes the answer is no. Actually, what we have is good enough, and so we don't actually need this more complicated, hard to work with model. And that's something that I feel is probably more common in industry settings where you're expected to maintain and reuse these models repeatedly, versus maybe more in academic work where you like research is the primary objective, and maybe you don't need to think as much about like model maintainability or productionization, things like that. And so I feel, yeah, like having a holistic perspective on how your model is evaluated is, I think, very important, and definitely something that, not any single metric is going to allow you to do that.
Yeah, definitely. And I'm really happy to hear that you guys use simulation-based calibration a lot, because that's quite new, but is so useful, right?
It's very useful. Yeah,
So,
it's nice to figure out if you have problems with your model before you fit it to real data.
yeah. Yeah, I'm curious about how you do that. But first,
Mm.
for folks who want some detail about that, you can
Mhm.
go back and listen to episodes 107 with Marvin Schmidt. We talked about amortized Bayesian inference and why that's super useful for simulation-based calibration, and also episode 109 with Sonia Winter, where we actually go into how would you implement simulation-based calibration and why that's useful. So it's a bit of context here if you don't know what that is about. And now there are chapters to the episodes. So if you go to the website, learnbasetstats.com, you go to the episode page, you'll have the chapters of the episode, and you can directly click to the timestamp, and you'll be able to jump directly to the episode, to the part of the episode where we talk about that stuff in particular. And of course, you have that also on the YouTube channel. So now, if you go to any YouTube episode, you click on the timestamp you're interested in, and the video will just get there. So that's pretty cool to reference back to something, you're like, oh, I've heard that somewhere in the episode, but I don't remember exactly where. So yeah, like something you can do that I use actually quite a lot. You go to Learn Base
Yeah,
Stats.
I'm going to be using this now. This is a good
Yeah,
tip.
you can do Control F. You do Control F and you look for the terms you're interested in, and it will show up in the transcript, because you have the transcript now also on each episode page on learnbasetstats.com. You look at the timestamp, and then with the timestamp you can infer which chapter this is talked in, and then you get back to the part of the episode you're interested in much faster. So yeah.
Yeah, very helpful, because searching in podcasts has historically been a challenging problem.
Yeah. Now that's getting much better. Yeah. So,
nice.
Definitely use that. I do that all the time because I'm like, oh wait, we talked about that. I remember it's in that episode, but I don't remember when. So
Yeah.
like, I use that all the time. So yeah, maybe like I know we're running, like we're already at 1 hour and 15, but just can you talk a bit about SBC, simulation based calibration? How do you guys use that in the trenches? I'm very curious about that. That's
it's a good question.
Topic of mine lately.
Yeah, so we have like for pretty much everything we do, we have like pretty custom models that we use, pretty custom software. So we have like our own internal software that we've written to like make it easy for the style of models that we use. But yeah, we for any model that we do research on, or any model that we end up deploying in production, typically, we start with simulation-based calibration and like prior sensitivity analysis and that sort of thing. And so with simulation-based calibration, typically, because described our workflow earlier, where it's kind of like multi-staged, and so but there are multiple different models, like there are a couple different models along that pipeline. And so typically we will do SBC for each of those individual component models, just to see if there are any like clear issues that arise from any kind of subcomponent of our whole pipeline. And then we will also try to do it, at least for like in some cases we might be able to do it for the whole pipeline, but typically we might look at it for each individual model, and then for the whole pipeline we might look more like at like the calibration of the posterior predictions, for example, against the true holdout points. But yeah, SVC is really nice because oftentimes we do want to be able to interpret the parameters in our models. Let's say like if you really don't care about interpretation, maybe it's maybe not as motivating to go through the whole SBC process. But in our case, oftentimes we'll have parameters that represent like how much momentum a program has, how much reversion it has, like where the average program level loss ratio is that gets reverted back to is sitting, which is an important quantity. And we want to know that when we, get those numbers out of our models and the parameter values, that we can actually interpret them in a meaningful way. And so SBC is, a great way to be able to look and see like, okay, are we able to actually estimate parameters in our models in an unbiased and an interpretable way? But then also like, have we programmed the models correctly? I think it's another big thing SBC helps you resolve, because often, the only time you really know if your model is actually coded up the right way is if you simulate some fake data with known parameter values and then try to recover them with the same model. And SBC's sort of just like a comprehensive way to do that. I remember like before I read this SBC paper, I used to, back in my PhD years, like we would, pick a random set of parameter values for these models and simulate some data and refit just that single set of parameters and see like, okay, like are they falling in the posteriors? And I feel like SBC is sort of just like a very nice way to do that in a much more principled way. And so I would definitely encourage regular use of SBC, even though it takes a little bit more time, but it saves you more headaches later on down the road.
Yeah, I mean, SBC is definitely just a industrialized way of doing what you described, right? Just fixing the parameters, sampling the model, and then seeing if the model was able to recover the parameters we used to fit it, basically. I mean, from these parameters, you sample prior predictive samples, which you use as the data to fit on the model. Amortized Bayesian inference is super useful for that, because then once you've trained the neural network, it's free to get posterior samples. But two things. First, that'd be great if you could add that SBC paper you mentioned to the show notes, because I think it's going to be interesting to listeners.
Oh, yeah.
And second, how do you do that concretely? So when you do SBC, you're going to fit the model, I don't know, 50 or 100 times in a loop. That's basically how you do it right now?
Yeah, usually we'll fit probably like 100 to 500 times, closer to 500 usually. A lot of our models actually don't take too long to fit. Most of the fitting time that is involved is in like the R&D process, like back testing, training the stacking models and all that. But once you're like, for the individual models to fit to data, they're pretty quick most of the time. And so we do a decent number of samples usually. And it's sort of like, we have like the way that it's programmed out in our internal software is that we'll like refit the model and basically just like save out all the sort of rank statistics that we need, or like the location of the percentiles of the true values and the posterior predicted values for those parameters, and just store all of those like going over in a loop. I think we might have some stuff that we've messed around with, like parallelizing that, but it ends up usually just being faster to just parallelize the MCMC chains instead. So a lot of times we just run this stuff locally, because the models fit so quick. That's usually how we approach it. But so it's like if you can set a single set of parameter values and do a parameter recovery simulation, SBC is basically just a loop on top of that. So it's a lot. It's not too much overhead. Really, the overhead is in like the added time it takes, not necessarily the added amount of code that it takes. Which is kind of nice, I think.
Yeah. The code is trivial. It's just like you need to let the computer basically run a whole night.
Go make some tea, get a coffee.
To do all the simulations. I mean, that's fine.
Keep your house warm in the winter.
Usually it fits quite fast, the model, because you're using the prior predictive samples as the data, so it's not too weird in general if you have a robust structure in your generative model. So definitely
that's a great point.
The listeners to do that.
Yeah, for sure.
And if you don't have completely stupid priors, right? Of course.
If you have you will find that you
priors,
probably do.
And if you're using extremely wide priors, then your data is gonna look very weird a good portion of the time, and so then the model fitting is gonna be longer. But then
that's a good point that I didn't bring up, but for helping come up with reasonable priors, SBC is another. So it's a good way to do that, because If it works, then that's a good sign. If it's going
Yeah,
off the rails, then probably your priors would be the first place to look, other than perhaps a
yeah,
bug in the code.
yeah. No, exactly. And that's why SBC is really cool. I think it's like, as you were
Yeah,
saying,
agreed.
because then you have also much more confidence in your model when you actually start fitting it on real data. So
Yeah.
yeah. So maybe one last question for you, Nate.
Yeah.
I have so many questions for you. Is like you do so many things, but we're closing up to the 1 hour and a half. So I want to be respectful of your time. But I'm curious where you see the future of Bayesian modeling, especially in your field, so insurance and financial markets, particularly with respect to new technologies like the new machine learning methods and especially generative AI.
Yeah, no, that's a great question. I'm of two minds, I think. Like a part of me, from doing some Bayesian modeling and I guess kind of like healthcare before this and now more in like the finance insurance side, I think there's like what you see in the press about like all the advances in generative AI and all of that. And then there's like the reality of the actual data structures and organization that you see in the wild. And I think I think there's still like a lot of room for more of what you might think of as like the classical kind of workflow where people are, uh, not really necessarily relying on any really complicated infrastructure or modeling techniques, but more following like your traditional principled Bayesian workflow. And I think especially in the insurance industry is like very heavily regulated. And like if you're doing a pricing for insurance, for example, you basically have to use a linear model. There's really there's really very little deviation you can get from there. And so like yeah, you could do Bayes there, but you can't really. I think more of like the what we might think of when we think of like AI types of technologies. I think there's potentially room for that in like within organizations, but for some of the like the core modeling work that's done that influences decisions that are made, I think there's still a ton of room for more of these like classical statistics types of approaches. Um, that being said, I think there's a lot of interest in like Bayes at scale and like more like modern machine learning types of contexts, and I think there's a lot of work that's going on with like in-law and variational Bayes and like the Stan team just released Pathfinder, which is kind of a new algorithm like on the variational side of things. And I think when I think of like Bayes at scale and like Bayesian machine learning types of applications, I think there's probably a lot of interesting work that can be done in that area. I think there's a lot of interesting future potential for those methods. I have less experience with them myself, so I can't really speak to them in too much detail. Uh, but I also think like there's a lot of interesting things to explore with like full Bayes, like with you know as we have more compute power, it's easier to like for example run a model with many chains with relatively few samples, and so I think with distributed computing, I I think it would be great to have a future where we can still do like full Bayes, like get our full posteriors with some variant of MCMC, but in a faster way, just with more compute. And so I think, yeah, so I guess all that to say, I think that there's going to be a long time before the classical statistics like modeling workflow becomes obsolete. I don't see that happening anytime soon, but I think in terms of like using Bayes and other things at scale, there's a lot of really exciting different methods that are being explored that I haven't actually myself had any real exposure to in like work setting or applied setting, because the problems that I've worked on have kind of retained their I can still mostly fit the models on my laptop or on like some some EC2 instance that some computer that doesn't require too much compute. So yeah, I guess that's my current perspective. We'll see how it changes.
Yeah. I mean, these are good points for sure. Like, I mean, you're still gonna need to understand the models and make sure the assumptions make sense and understand the edge cases, the different dimensions of the models and angles, as we talked about a bit earlier. So, yeah, I think
Yeah.
that's a really tremendous asset and a kick-ass sidekick. So for sure, like that's extremely useful right now. And I mean, I can't wait to see how much progress we're gonna make on that front. Like I really dream about having like a Jarvis, like Iron Man, like Tony Stark has Jarvis, and then it's just like it's extreme. That'd be perfect, but where you basically outsource a lot of that stuff that you're not very good at, and you focus on the thing
Right.
you're really extremely good at and efficient and productive.
Yeah, no, I definitely think that like with a lot of the generative AI types of tools, there's definitely can aid with productivity for sure. Like
Yeah.
I can't tell you how many times I've just been like, "Hey, tell me how to do this with Pandas because I don't want to figure it out." Similarly with like Plotly or stuff like that. I feel there are certain parts of the workflow where Google or Stack Overflow is no longer the first line of defense, right? Um, and I think like a lot of that stuff that I don't like to spend time on sometimes can be sped up by a lot of these tools, which is really nice to have, I would say.
Yeah.
But yeah, we'll definitely be curious to see if Bayes underlies any of some of these methods going forward. I know there's an interest in it, but the
Yeah.
scalability concerns have so far maybe made that a little challenging.
Although I don't know in your case, but in my case, I've never had a project where we were like, oh no, actually we can't use base here because the scale is too big.
Right. No, I agree. I think I've been similarly for me. Usually there's a way, and I think uh, yeah, I think there are definitely problems where that gets challenging. But at the same time, like if it's getting challenging for Bayes, it's probably going to be challenging for other methods as well. I think, and then you deal with other issues in those cases too. Uh, and so I think yeah, I think I've also been kind of biased by this because a lot of times I'm working with rather small data sets, at least in terms of like the like how much memory they're taking up on my computer or something like that. Like
Yeah.
they're small enough that we can do some fun modeling and not have to worry too much. Yeah.
Yeah. Yeah. No, I mean that's a good point. But yeah, definitely, I'm still waiting for a case where we'll be like, oh yeah, no, actually, we cannot use base here.
Right. Yeah.
So
Yeah.
yeah, that's actually interesting.
Hopefully it never happens, right?
Yeah, that's the dream. And so, well, Nate, let's call it a show. I've already taken a lot of your time and energy. I'm guessing you need a coffee.
Oh yeah, I'll probably go get some tea after this. Maybe a Red Bull. We'll see how I'm feeling. But no, this has been a great time. I'm excited.
Yeah, no,
But
it was great. I mean, of course, I'm gonna ask you the last two questions. I ask every
oh
guest at the end of
yes,
the
yeah.
show. So, first one, if you had unlimited time and resources, which problem would you try to solve?
Yeah. So I've thought a lot about this because I've listened to the podcast for so long and I contemplate it every time. I feel like I always miss the other listeners' responses because I'm lost in my thoughts about like how would I answer this? And I think probably um, I think I would want to do some work in like mental health, which is sort of the field that I grew up in, right? Um, like there's a lot of like open problems in like psychiatry, clinical psychology, both in terms of like how we measure uh, like what a person is experiencing, like mental illness in general, how we dissociate different types of disorders and things like that, but then also in terms of treatment selection, as well as like tiered treatments, like automated treatments that are maybe scaffolded through like apps first, or that have different types of models rather than just like the face-to-face therapy model. And I think, yeah, if I had unlimited resources, unlimited time and funding, I would be exploring kind of solutions to that, which I guess solutions isn't even the right word, but ways to kind of approach mental health crisis and how to measure, but both better measure and better get people into treatments that they need. And some of the work I was doing at AVO before was related to this, but it's a surprisingly hard field to get funding for, just because there's a lot of barriers. Working in like healthcare is a hard thing to navigate, and there's a lot of snake oil treatments out there that seem to suck up a lot of the interest in funding. And so I think, if I didn't have to worry about that, there'd be a lot of interesting things to do. But yeah, I think that would be what I would focus my energy on.
Yeah, definitely a worthwhile quest. And since you never get the listener, the guest's answers, I think you're the first one to answer that.
Oh, right, yeah. I feel it goes with my my Freudian sips mug here. It's my favorite one.
And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, this one was a lot harder for me to think about, but I came to what I think would be the answer, and so I'm going to pick a fictional person. And I don't know if you've read Foundation series or like watched the television series, but Hari Seldon, he's the architect of what he calls psychohistory, which is essentially the science of predicting like mass behaviors, like population level behaviors, and he's like developed this mathematical model of that allows him to predict, thousands of years into the future how people will be interacting, and like saves the galaxy, all that, spoiler alert, but sort of. I'll leave some ambiguity, right? But I think that would be the person, just because it's kind of an interesting concept. I think he's an interesting character, and like psychohistory sort of is like, given my background, I'm just kind of interested in that whole concept. And so if someone were able to do that, I'd sure like to better understand how exactly they'd be doing it. Maybe there's Bayes involved. We'll see.
Yeah, great answer. And here again, first time I hear that on the show. That's awesome. You should definitely put a reference to that show in the show notes.
Oh, yeah.
That sounds like fun. I will
definitely
gonna check that out. And I'm sure a lot of listeners also will. So yeah, definitely. Well, awesome. Thanks again, Nate. That was a blast. I really learned a lot, and that was great. I think to have an updated episode about model averaging, model comparison. I hope, Stefan, you were happy with how it turned out to be.
Me too.
Well, as usual, I'll put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Nate, for taking the time and being on this show.
Awesome. Yeah, thanks a lot for having me. I had a blast, and look forward to being a continued listener.
Yeah, thank you so much for listening to the show for so many years. That definitely means a lot to me. And you're welcome back anytime on the show, of course.
Yeah, just let me know.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasestats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.